Hello again, and welcome to the another set of video on microcontroller technology. This subtopic being microcontroller assembly programming. Uh, I need to take you through this because the subtopic was not covered in our class session. So I hope this video will be able to help you understand on microcontroller assembly programming. So we'll dive to the notes, whereby I've looked at the definition of microcontroller programming. By the basic definition, I've said is an art and science that involves writing instructions or command that tell a microcontroller on what to do. So that is basically the simplest definition of how you can define a microcontroller programming. So before you start programming and know the difference, the different types of programming languages that we used in microcontroller programming, we also have to understand some common definitions which are commonly asked in our series of exams. Number one is it's an instruction set. Always remember that all questions that are asked on definition of terms, we always use a prefix it refers to or it is, to show that it's a definition and you are defining something by referring to it. So if you are asked to define instruction set, you can say it refers to a complete set of commands that a particular process or microcontroller can understand and execute. Each command performs a specific task. So that is how we can define an instruction set. Then you have an assembly language. It refers to a low-level programming language that directly corresponds to a processor's machine code. It uses short, easy to remember codes referred to as mnemonics to represent instructions such as move for move, add for add, etc. So that is how we can define an assembly language, and you'll discover that most microcontroller, or in our microcontroller programming instruction, we always use low level instructions to write codes that can instruct a microcontroller on what to do. Then we have a high level language. These are more complex instructions or commands which involve a special device such as a compiler to translate them into a machine understandable by the microcontroller. Examples include C, C++, Python, etc. So high level programming languages are more complex instructions, and most of the time there is that shift whereby someone can write a program using a high level language, but he wants to direct a machine that uses a low level language. So he'll have to use a device that can be able to interpret that high level language into a low level language, so that it can be able to be used by the microcontroller and instruct that microcontroller to perform a specific task. Consequently, there can be a code that has been written using an assembly language, which is a low level language, and it needs to drive, or it needs to instruct, a device that has been programmed by a high level language. So it means they will also have to use a device that can be able to translate the machine code or the low level language into a high level language, so that it can be perceived by that device that uses a high level language to perform its operations. So after knowing high level language, the next definition is an assembler, whereby it refers to a program that translates an assembly language code into a machine code or binary instructions that a processor can execute. Then we have a compiler, which is the opposite of an assembler, which translates a high level language code into a machine code. So that is those are the 5 definitions of terms that one, or as a learner, you need to know when you are talking about microcontroller programming. So if I move to the next slide, we have our next subtopic talks of common commands used in 8085 microcontrollers. So here we want to look at what are some of the basic commands that we always use in microcontrollers to write a program or an instruction that can enable a microcontroller to perform a specific task or to execute an activity. So I've always grouped them into classes. whereby I have a class A, which is a data transfer instruction. So if you look at my description, says these commands enable the movement of instructions between registers, memories, and input or output devices. So they just necessitate the movement of instructions or data between the devices that are being involved. And more examples of data transfer instructions, it can be one which is move r1 comma r2. You always have to remember when reading a code or a command, you always start from the right going to the left. So it means you're moving data, or you're moving the contents of the register 2 to register 1. So that one falls under data transfer instruction because it just involves data between two registers. We can have an mvir comma data. So it's an immediate command which says you move immediately the contents of a data into register R, and you find most of the time that data has to have a specified address which has a definite number that is labeled on it. So you can look at an example of an mvi r comma data, whereby in brackets I've said mvi a 05 hexadecimal. It means you move immediately the contents of data that are present in 05 hexadecimal port into the accumulator, which is always our main register and is always our register A. The next command, you have an LDA address, LDA in caps, then comma address. It means you load the accumulator with data from a specified memory address. Then you have STA address, you store the contents of the accumulator data into the specified memory address. Then you have capital LXAIH comma 2000 hexadecimal. So if you see a H, then it means we are looking at the register pairs. You have those types of registers that work as a set or a pair. So it means you're loading the contents of port 2000 hexadecimal into a register which is a pair register. Then you have the SHLD caps address. It means you're storing the pair register contents directly into the memory. Then you have an LHLD address, you are loading the contents of the register pair directly from the memory. So that those forms as our data transfer instructions and examples of commands that we use under microcontroller programming when dealing with the transfer and exchange of data or movement of data between registers. It can be between memories, it can be between input and output devices. Then we have a class B, which is an arithmetic instruction. These are commands that are responsible for performing any arithmetic calculations. So we have add R. This means that you add the contents of register R to the accumulator. If you look at that instruction, the accumulator has been addressed indirectly. So you might find yourself, maybe you're performing a certain activity, and that activity has a certain series whereby you need to have the result to be stored in an accumulator temporarily in order to use that result for another purpose or another process that has to take place subsequently. So you can use add R. Then you have sub R, sub in capital, then R, it means you subtract the contents of register R from the accumulator. Then you have an INR R, it means you increment the contents of register R by 1. This one applies to, we have specific incidences or cases whereby you can be told to add two numbers, maybe one in port 2001 and another in port 2002, and store the result in port 2004. It means port 2003 has been left, it has been jumped or skipped. So maybe that port might be active, it is performing another different activity, so you do not have to disturb that operation. So what will we do? After you do the calculations, you'll have to increment by skipping that port in order to now store the result to the next port that is available, and it's maybe empty or dormant. Then you have DCR R, it means you decrement the register R by 1 Then we have ADI caps data. It means you add immediately data to the accumulator. SUI data, it means you subtract immediately data from the accumulator. We have one capital DAD. RP, it means you double add the address register pair to HL pair. So that forms our class B, which is an arithmetic instruction. We have a class C, which is a logical instruction. They perform bitwise logical operations, whereby you have an example as ANAR. It's a logical AND get register with the accumulator. So if you look at that, the accumulator is it has been specified from that. Then you have an ORA R. It's a logical OR register R with accumulator. Then you have an XRAR. It's a logical exclusively OR register with accumulator. Then you have an capital CMA, which means you complement accumulators once complement. Then you have a capital RAL. You rotate the accumulator left through carry. RAR, you rotate accumulator right through carry. So that is also another set of logical instructions. Then you have branching or control transfer instructions, whereby they change the flow of a program execution. An example being JMP address. It's an unconditional jump to a specified address. Most of the time you can use an increment or a jump to skip one port. Mostly it is occupied by another function or no. We have call address, which is an unconditional call. A subroutine at a specified address pushes by the program counter onto a stack. Then we have RET, return from subroutine. Pops PC from stack. JZ, addresses jump if 0 flag is set. JNZ, address jump if 0 flag is not set. JC, address jump if carry flag is set. JNC, jump if carry flag is not set. We have another class, which is stack operations. For stack operations, we have two major instructions, because it can either be a push or a pop. If you look at the last time I was discussing about the operations of a stack pointer, I was looking at the pushing and the popping, if you remember that table that I used in class. So it pushes the register pair contents onto the stack, and you have pop, it pops the register pairs onto the stack. Then you have the input and output instructions. They communicate with the input and output devices. You can have an input address. It means they input data from a specified input or output port onto the accumulator. That specified input or output port has a definite address. Then you have an output port address. We output data from the accumulator to a specified input or output port that has a designated address. So that is our class F. Then we have the machine control instructions, which controls the CPU operations. HLT, hold the processor. No is no operations. The processor does nothing for one instruction cycle. So we have an example there, whereby I've said write an 885 assembly language program to continuously toggle an LED connected to 0 bit of an output port, e.g. port address 01 hexadecimal. And I remember always, most of the time, if you want to solve easily these programming languages, before you tackle that question, always try to interpret the question by writing the sequence. Know the sequence of how the program is flowing. And the key word here is toggling. Toggling means a change of state from one state to another. And for our case here, it's an LED. Then it means the LED can either be on or off, and the cycle has to repeat itself continuously, because there is no definite value or a definite time duration. And the first thing that I always said is since a microcontroller is a digital device that works almost the same as a counter. You remember the time we were talking about counters in the ladder diagrams? We said that the counter has to return back to its normal position by resetting, in order to allow now it to pick the program afresh from the start. So since a microcontroller is an example of a digital electronic, then we have to organize that microcontroller in such a way that it returns back to its default settings or reset so that now we can start the program. So if you look at that, then it means if I am to make this LED to change the state continuously, indefinitely, until maybe a time when I'll have to switch off the power, disconnect the LED from the source, then that is when the LED will go off completely. Then I'll have to use these commands. First, I'll have to organize my microcontroller. That is always my first step, to organize my microcontroller in order to form the start of my program. I'll have to use my accumulator, because my accumulator is always my main register, to temporarily store my data that I've achieved, because it will be required for the next state. I have to identify the ports that will be used for turning my LED on and the port that will be used for turning my LED off. I'll also have to introduce a delay, because that delay will have to signify the amount or the time duration my or maybe the seconds that my LED will have to turn on before turning off. At the same time, the seconds that the LED will turn off for a period of time, then turn on. And then after that, I can use jump so that it jumps back to my starting point and start again, or I can use return and end my program. So after knowing that, I'll start by writing the program by organizing 000 hexadecimal. This now will be my start of the program from this memory address, and now my microcontroller will be reset to its normal to its default setting, so that it can also pick up the program afresh. After now initiating or organizing the microcontroller, my next step will be to move the contents of the port that have been specified here. For our case here, have been specified a port address of 01 hexadecimal. So I'll have to move immediately the contents that have been stored in 01 hexadecimal into the accumulator. And basically the content that I'm being put into the accumulator is the one that will have to turn my LED on. So that is the command that will always turn my LED on. So if I move to them, then I will get an output through the same port that will make the LED to turn on. So I'll have achieved my first part, but now I'll have to toggle, because I've not justified the toggling. I have to change the state. So I'll have to go use a program that is called a branch program. If you look at it, it's a branch or control transfer, because here we are looking at how we can control an LED to turn either on or off. Then I'll have to use a branch whereby I'll call a delay, such that that delay will enable this LED to turn on for a specified short period of time before turning off. So I'll move that contents of the 0. I'll load the accumulator with the contents of 0 hexadecimal, which is another external output, and I'll get an output at point 01, which will now change the state of the LED to an off state. After that, I'll call a delay subroutine, whereby the delay will let the LED to turn off for a specified period of time, then turn on again. And since I'll have used port 01 hexadecimal, I can use another branch or control transfer function, which is jump, to start, such that it will jump back to its starting position, which was at 00, then continue the same process. Another person can use a return, whereby it can return to its initial step, but mostly returning, it means it will return using the same procedure that it went, but jumping and coming back to its starting point, it will act very efficiently, because it looks like the program at least makes sense. But you can use return, whereby it can return to its start, then it will repeat indefinitely, and then you end the program. So that's how you'll have written the program, to show how you can continuously toggle an LED connected to bit 0 of an output port indefinitely. So this LED will keep on doing this until the time when the power is either switched off or it's disconnected from the source. So that is an example of how you can write an 885 assembly language to continuously toggle an LED and then connected to a bit 0 of an output port. So we have another example, which is write an 885 assembly language program to add two 8-bit numbers stored in memory locations 2000 hexadecimal and 2001 hexadecimal. Store the result in memory locations 2002. Assume the sum will not exceed 255. So the solution here, and if you look at most of my microcontroller assembly language, I always write a sequence that will enable me, or it will guide me in writing the program. So this is a type of a program whereby I was telling you have to use the increment, because it will be of a very great essential when doing this. If you look at the locations that have been speculated here or mentioned, we have 2000 and we have 2001 and we have 2002. So you'll have to look at incrementing, because if they are increasing the registers by 1, so I'll have to use another program of increment. So before I tackle the question, I'll have to determine the sequence of the program. So I know that I have to organize my microcontroller to its reset. That is always my first step. The next step is I'll have to use my accumulator, which will be storing my data or the contents of my program temporarily in order to be used for another sequence. So in here I can say initially the program, or maybe the microcontroller, has to be returned to its default state. So I'll have to organize my port, which is my starting point from the memory address. Then I'll have to load the accumulator with which is our main register, with the first number, because if you look at the first number, I'll load it to my accumulator. Then the second number, I'll load it to another address, and then I'll have to store the results in the accumulator as I wait to store it into the target memory location. So if I write the program, I'll start by organizing the microcontroller, which is organizing 000 hexadecimal to form the start of the program from the memory. Then I'll have to load immediately the contents of 2000 hexadecimal. If you look here very keenly, we have add two 8-bit numbers stored in the memory location. So it means if it's a 2-bit, we have a pair. So I'll have to load the HL pair register with 2000 hexadecimal, which will form my first address. So loading, but it's before I load to the accumulator, it's like I'm trying to inform the accumulator that the contents that I want to load them after that, they are acting as a pair, so the accumulator can be able to accommodate those contents in the form of a pair. So after loading the contents into a register HL pair, which is my first address, I'll have to move the contents into the accumulator, and the contents that I'm moving are the contents of the HL pair register, or in brackets the 2000 hexadecimal, into the accumulator. And since they have formed my first number, the second address, it is at port 2001, so it means I'll have to increment my current register, my current memory port, which is a 2000 hexadecimal, by 1, and that's why I've used an increment L, whereby I'll increment the contents that are present in the register pair to point, or the contents that are present by the HL pair registers, which have a designated address 2000 hexadecimal, to point to the second register, and that second register is at memory location or port 2002. That is where I'll perform my addition. So I'll add M, which is the contents of the memory pointed by the HL, and I'll store the result in the accumulator. So I'll store it temporarily in the accumulator, waiting to point to the target memory location, which is my final memory that I have to record or store the additions of the two. So if you look at keenly where I have to store the addition, it is at 2002. So which means I'll have to also increment the current register that that I've done the addition, which is 2001, in order to store now the result to the target location, which is 2002 hexadecimal. And that's why I've used an increment L, which has the contents of the HL pair registers to point to the register location or memory location 2002 hexadecimal. Then alternatively, a person can end from there. You can continue and say hold the processor because you'll have already achieved the addition, or you can use another movement whereby you can move the contents to the accumulator to stay there temporarily as they wait for, maybe you can keep them for future storage and so on, and you can hold the processor and end the program. So that is also how you can write that program, which involves the addition of two 8-bit numbers stored in memory locations, different memory locations, but now they have variations whereby the memories are arranged in a sequence that keeps on increasing by 1. So it means you have to use an increment command. So that is the end of the microcontroller assembly programming languages. Hope these assumptions help you to understand at least on what is expected of a microcontroller instructions and how can we write the programs, and you can be in a good position to answer them. So that is just how we use these programs and these commands. Most of the time you can find them in the back page of the question paper. You can use them to write the commands and so on. So that is just the trick. For me, the only trick that I always say in any microcontroller programming question is that when you're given a question is always write the sequence. Just scribble a sequence, know what sequence I have to follow. After that, know what instructions or commands I'll use. After knowing what the commands I'll use, know how the sequence or writing the commands will look like, and you'll be good to go. So I think that marks the end of microcontroller assembly programming, and hope it helps in a revision. All the best.